So yesterday we did the introductory parts of thermodynamics, learned the definitions of a few terms, and we started with lecture 2, the properties of pure substances. So we spoke about what a pure substance is. We spoke about the phases, and we also looked at some diagrams. So temperature against specific volume, then pressure against specific volume. So we spent some time to really talk about what is happening here and what is happening here as well. So this is where we ended yesterday. So before we continue, are there any questions from what we did yesterday before we move on to the rest of it? Okay, and I think we can carry on. Okay, so someone said you should take the diagram again. I think we'd use this diagram and then we'll use it to explain what we are looking at, right? So this is what we were saying. When we have a particular species, a particular compound, a particular substance, we can look at the effects of pressure and temperature on it. So what we have here is we have a graph of pressure against volume, and we are considering that we are keeping the temperature constant. So we can have different lines. We call them isotherms. We can have different isotherms, right? So isotherm is just a graph that is being plotted at constant temperature. So we have here our pressure against a specific volume. Now, what we are seeing is that if I'm starting, let's start from this point here. So let's say I'm starting out as a gas. I'm keeping the temperature constant. Realize that over here, I have a very high specific volume for the gas, but then the pressure is lower. So as I increase the pressure, what's going to happen is that the molecules are going to be pushed closer to each other. Then it gets to a certain point where now the molecules are so close to each other that it now starts condensing to form a vapor, sorry, to form a liquid. So at this point here, it is a saturated point. We have the vapor, but then it's at the verge of becoming a liquid. So remember we said when phase change is being done, temperature and pressure are kept constant. So the temperature and the pressure here are not going to change. That's why we see the line to be horizontal. The pressure is not going to change. But then along that line, as the gas is becoming more and more a liquid, the volume will be reducing more and more until we get to this point here. Then if we should increase the pressure further, then the volume or the specific volume would reduce even more. But then the reduction is slight. It's very small because now we're in the liquid region. When we compress liquids, we don't really see a significant reduction in the volume. So that's what we spoke about yesterday. That's where we ended yesterday for the pressure and then the specific volume diagram. I hope that's fine. We'll take it from there. Okay. So we are saying here that when the pressure of a phase mass of water vapor is increased, the volume of the water vapor will decrease. So that's what we spoke about. And it continues on to the vapor is saturated. So that's when it gets to this point over here, right? And at this point, we can have the specific volume reducing without we necessarily affecting the temperature or the pressure or causing a change in the temperature or pressure. So it will now start becoming more of a liquid. Then it gets to a point where now it's liquid, but then it's also still saturated. So if we further reduce the pressure now, increase the pressure, would have the specific volume reducing again. Right? So it's similar to what we spoke about for the temperature and then the specific volume. It's just that for the temperature, we had to rather increase the temperature. So for that one, the diagram was going this way instead. So for that one, it went this way instead. Then it became horizontal and then it continued upwards. So we spoke about all of that yesterday. Okay, so I think we can take it from there. Sure. So now we can also apply this to solids as well. So all we've done so far is we've just considered the liquid and then the vapor points. But then there's also a point where we can have the liquid becoming solid. So realize that if I have a liquid and I should continue to reduce the pressure, so I should continue to increase the pressure. I can increase the pressure to a point where now it begins to solidify. So that's what we're also talking about. As we are increasing that pressure, remember we said for liquids, when we compress them, we don't see a significant change in the specific volume. That's why the line looks almost vertical. And then down here, too, we see that it's almost vertical. So the change in the specific volume is very small, or it's almost negligible. But then we can increase the pressure to a point where now we can have it moving from liquid to solid. So when we have these diagrams, it just helps us define the regions where a material will be at different phases. So if we are maybe at a pressure here and then a specific volume here, we know that the substance we are dealing with is a solid. Once it crosses this line and it gets here, it's a mixture of solid and liquid. When it gets to this region here, vapor. So when it gets to this region in the middle here, then it's a mixture of liquid and vapor. So these graphs help us determine the phase that we'll be expecting under different conditions, right? So it's important to take note of that. And one thing to note is that whenever you fall on the line itself, then you are saturated. So what we mean by that is if I should fall on this line here, right, then I'm a saturated liquid. I'm at the verge of becoming a vapor. Once I cross that line and I get into the space here, then I'm a mixture of liquid and vapor, right? If I'm on this line here, because this is the vapor point, I'm moving from vapor. Once I get to the line, I'm a saturated vapor. So I'm at the verge of becoming a liquid. Once I cross the line, then I'll have liquid droplets forming. So I'm now a mixture of liquid and vapor. The same thing happens down here. So here I'm a mixture of solid and vapor, right? And when I cross the line, I'm now going to be saturated. And then if I should go a bit further, I'll now start having liquid also coming in there. So this line down here, we call it the triple line because at the points on this line, we can experience the triple point of the substance. That's the point where the substance can exist as solid, liquid, and vapor. So all we are trying to say is that um, these graphs help us determine the phases that we are looking at for certain pressures or temperatures or conditions that we have. When you are in a region, then you are defined by what we see in that region. So if you are here, you are solid. But once you fall on the line, depending on the direction you are coming from, you become a saturated um, material. So I will be a saturated liquid, saturated vapor, depending on where I am. And if you are saturated, it just means that you are at the point where your phase can now begin to change. Is that okay? Okay. Now we can also um plot graphs for pressure against temperature. So all that we've seen so far was pressure against volume and then temperature against specific volume. But you can also do the same thing for pressure and then temperature. So realize that at very low pressures and very low temperatures, I can have my material in a vapor phase. So that's down here. So the pressure and temperature are very low, right? If I increase the pressure a bit for some substances, I can have it solidifying directly from the vapor. So that line here is going to be the sublimation. And because that sublimation is just looking at the change from solid directly to vapor without passing through the liquid phase. So very low pressures, very low temperatures, I'll be a vapor. Just a little increase in pressure can cause me to become a solid, right? Or at very high temperatures and very high pressures, I can be a vapor. Then when I reduce the temperature a bit, I can become a liquid. Is that okay? And for these two lines here, it depends on the kind of substance you are dealing with. If it's a substance that would expand when you are reducing the temperature or you are freezing it, then the curve goes that way. But if it's a substance that will contract when you are reducing the temperature, then the curve goes this way. So once again, these graphs just help us determine the kind of phases that we are going to have as different conditions of temperature and pressure. And then we can also do it in a three-dimensional way as well. So we can make it a graph of pressure specific volume, and then temperature. And then when we join all the points, maybe I have a specific pressure, a specific volume, a specific temperature. When I trace all of them to the graph, I'll be able to determine the particular phase that it is in. Is that okay? Please, is that okay? Okay. So we have more examples here. So this is one for water, a phase diagram for water, and we have one for carbon dioxide here. So now let's look at what is happening on the diagram for water. So what we are seeing is that down here, the brown parts, everything here is going to be a vapor. So that's with um very low pressures, low temperatures, or very high temperatures and very high pressures. So everything from this point up to this point. There's a particular temperature and pressure that if you work with, your water would be a vapor, right? So if I'm at 100 degrees Celsius and I'm at maybe 0.6 kilopascal, so this 0.6 kilopascal, if I should trace this to meet the 100 line, you realize that I'm still in the vapor region. So at 100 degrees Celsius and 0.6 kilopascal, my water will be expected to be a vapor, right? But then if I'm at 100 degrees Celsius and then I'm at maybe, let's say, 105 kilopascal, so let's say that's somewhere here, and then the 100 degrees Celsius line was here, realize that now I'm going to be a liquid. Is that okay? So you are able to determine the phase of your material based on the temperature and then the pressure. But now let's consider something else. Look at the case where now we are at 100 degrees Celsius and then we are at 101 kPa. Realize that you are on the line. Remember we said when you're on the line, you are saturated. So now you're a saturated liquid or a saturated vapor, depending on where you're coming from. So if I'm coming from the vapor point and I get to the line, I'm a saturated vapor. It means that now I can have liquid droplets forming, right? If I'm coming from the liquid point and I get to the line and I'm a saturated liquid, it means I can now have vapor droplets forming. Sorry, vapor bubbles coming out. Remember we said if you are saturated, it just means that you're at the point where your phase can begin to change. Is that okay? Okay. A minute. So all we are saying is that with these diagrams, you're able to determine the phase of your material based on a given temperature and a given pressure or based on certain conditions. So if I have water at 100 degrees Celsius and I have the pressure to be, let's say, 0.6 bar, you just trace the temperature and then the pressure points. And where they meet, you'll be able to determine the phase. So if I should trace the 0.6, it will meet the 100 degrees Celsius line in the vapor region. If I should have maybe 200 kPa and 100 degrees Celsius, it will meet the 100 degrees Celsius line in the liquid region, right? If I should have 100 degrees Celsius and then 101 kPa, they are meeting on the line. If they meet on the line, then it means it is saturated. Saturated means that the phase of the material can now begin to change, or it's at a point where you can have two phases coexisting. So liquid and vapor can coexist, right? So if I'm moving from the vapor region, then it means I'm a full vapor. I'm totally vapor. But then as I'm going upwards, I get to the line. Now, because the line is for saturated materials, it means that I'm no longer going to be just a total vapor. I can now have liquid droplets forming. And then in the other way, if I'm rather coming from the liquid points, maybe I'm already a liquid, and then I change the conditions such that I get to this line. I'm no longer going to just be a liquid. I'm going to be a liquid that can now start having vapor bubbles forming. Is that okay? So someone is asking that the saturated point, does the phase always change to vapor? It depends on the regions you are considering at the boundaries. So this is what we mean by that. If it's a liquid here and it's a vapor here, then the saturated line in between them is going to be a point where you can have liquid and vapor. So the liquid can change to vapor, the vapor can change to liquid. But if the saturated line was the one we have here, the one between the solid and then the liquid phase, or the melting line, what's going to happen is that I can have on that line, I can have solid being changed to liquid and liquid being changed to solid. So it depends on the regions you are dealing with. Is that okay? Okay. So that's it. Right. So the conditions of temperature and pressure would allow you to determine the phase of the material. Now, this point down here is called the triple point. The reason is that if you look at it, it's serving as a form of boundary between the solid, the liquid, and then the vapor, right? So at this point, I can easily move into the solid, the liquid, or the vapor region. So it means that at this point, both solid, liquid, and vapor can exist together. So that's why it's called a triple point, right? Now, when we consider the graph for carbon dioxide, we can see another region here, the green region. That's for supercritical fluids. So it's for fluids that have very high temperatures and pressures. So, so for liquids with maybe very, very high temperatures, we can have them to be supercritical. So we spoke about critical fluids yesterday as well. Okay. So we can have diagrams for other materials. You can also have one for ammonia. You can have one for nitrogen as well. So you can look at the temperature and pressure and determine the phase. So I would send us some questions where we would have to determine the phase of the material at different conditions so that we can use that for practice. Okay. A minute. Okay. So we can continue. Now, what do we know about the phase transitions? What do we know about the liquid vapor transitions? So this was the curve we had for pressure against the specific volume. And you remember that we said we have different regions. So we have a region where we said we are just going to be a liquid. So a compressed or a subcooled liquid, right? Or we have a point where we are now saturated. So here we can have liquid and then vapor together. And then we can have the points where we are just vapor, but then we are superheated, right? So the reason why this side is called subcooled, or the reason why it's called compressed is that usually it would work with points where we have very low temperatures relative to the temperature that it would have just been a normal liquid, right? So maybe it's a little bit below the room temperature, or we've increased the pressure a bit, so we can keep it in a liquid form. But remember that for liquids, when you compare them to gases, the pressures of the liquids, or I mean, if you have a material and want to keep it as a liquid, you might have to increase the pressure or reduce the temperature. So compressed because of the increase in pressure, subcooled because of the reduction in temperature, right? So it depends on the particular thing we do. If we are increasing the pressure to keep it as a liquid, then it's compressed. If you are reducing the temperature, then it's a subcooled, right? So that's this region here where we have a liquid. Then we get to the points where now it is saturated. So we can have a mixture of liquid and vapor. And then we have this point here where it's a gas. So a further increase in temperature will cause it to become superheated, right? So when it just becomes a vapor, then it's a vapor. But then when we increase the temperature further, then we can have it becoming a superheated vapor, right? Or even when we increase the pressure, we cause it to become a bit superheated. Is that okay? Okay. Yeah. So when we reduce the pressure, yeah, okay. Then we can also talk about vapor pressure. So when we are talking about vapor pressure or saturated, the saturated pressure of a material, what we are seeing is that is the pressure at which the material can now start to boil. And it happens when the pressure of the liquid becomes equal to the pressure of the atmosphere or the surroundings, right? So if we have um a minute. Yeah, so if we have a particular material, like maybe water, you know that at these conditions, it's going to boil. The reason why it's going to boil is because the pressure that is being exerted by the um gas bubbles that are being formed is equal to the pressure of the atmosphere, right? So that's where we have vapor pressure. So it's defined as the pressure exerted by vapor in thermodynamic equilibrium with the condensed phase at a given temperature in a closed system. So there's a particular temperature that we are working with that is going to cause it to now start becoming a vapor, right? Or to now start boiling or now start becoming a vapor. So now we have that vapor and then maybe a liquid in equilibrium now. Is that okay? So substances that have high vapor pressures, they are called volatile because now they can become more of a vapor under those conditions. Is that fine? Please, is that okay? Okay. And I think we can carry on from there. So we are seeing here that the vapor pressure of any substance will increase non-linearly with temperature and then the atmospheric boiling point of a liquid, also known as the normal boiling point. So it's the temperature at which the vapor pressure would equal the ambient atmospheric pressure. So that's the definition for the boiling point, where the vapor pressure of the material, the pressure that would be exerted by the material at a particular temperature is equal to the atmospheric pressure. Then we have boiling occurring, right? And then if we should increase the temperature, that vapor pressure can become enough to overcome the atmospheric pressure. And then the liquid will now form bubbles that can now come out of the substance. Okay. So when we want to determine vapor pressure, for most materials, we have certain constants that we can put into this equation called the Antoine equation. When we put them into this equation, it helps us to determine the saturated pressure or the vapor pressure, right? So they have already been determined by experiments. We know the constants for A, B, and C. So we can put in the particular temperature we are looking at and then make P the subject to get vapor pressure or saturated pressure. Is that okay? Okay. So that's the Einstein equation here. The constants, we can get them from tables. So we put them in, we make P the subject, and put in a temperature. But one thing to notice is that whatever table you are using, whatever reference you are using, okay, there are some questions, I'll answer them. Whatever table or reference you are using, please check the units very well. If they are giving you the constants and they are working with the temperature in Celsius, make sure temperature is in Celsius, degrees Celsius. If it's in Kelvin, make sure it's in Kelvin. So someone is asking that saturated vapor pressure is the same as the vapor pressure. Yes, yes, you're saying it's the same thing. Then another person said they didn't get something. Can you please indicate the specific part? This page. Okay, so what we are saying is that if you want to determine the vapor pressure or the saturated pressure of a material, sometimes we can use this formula. So there are tables that have constants for A, B, and C for a particular material under certain conditions. So maybe for water, there's a constant for A, there's a constant for B, there's a constant for C. So we just put them in, and then we put in the temperature that the water is at. When we do that, we can just make P the subject, and then that will be the saturated pressure. Is that okay? So this is the Antoine equation. We have constants A, B, and C. We can get them from different references and tables. So we put them in, we make P the subject, and then we get the vapor pressure. Okay. But the one thing to note is that these constants work in a certain range. So maybe you might have water, but then the constants might work maybe from 25 degrees Celsius to maybe 300 degrees Celsius. It means that beyond 300 degrees Celsius, this is not going to give you an accurate answer, right? So you need to check your reference very well, the temperature range that it can work with. Okay. Now, there are other properties that we also want to consider aside just pressure, volume, and temperature. So we have internal energy, enthalpy, entropy, and then Gibbs energy. And for these properties, we can easily determine them when we know at least two of the properties before dealing with that pressure, volume, and temperature, specific volume and temperature, especially when we are dealing with pure substances, right? So for this course, for thermodynamics one, we are just going to focus on enthalpy, entropy, and then internal energy. We'll not consider Gibbs energy, right? And these properties, we look at them in an extensive form. So we spoke about extensive and intensive variables and properties yesterday. So they can be in an extensive form. And if we want them to be specific or intensive, then we can divide them by their mass or by their moles, and then we can have them in the intensive or the specific forms. Is that fine? Okay. So now let's look at the different kinds of, if someone says I should take it again. Okay. So what we are saying is that we've looked at pressure, volume, and temperature so far, specific volume and temperature for pure substances. But then there are other properties we can also consider. So we are about to speak about those properties. We can have internal energy, we can have enthalpy, we can have entropy. And what we are saying is that these properties can be extensive and we can make them specific or intensive by dividing by the amount of material we have, the mass or the moles of the material we have. So I can have just internal energy. If I divide it by the mass, it becomes specific internal energy. Or I can have just enthalpy. If I divide by the total mass of the material, I can get the specific enthalpy. So that's what we are saying. Okay. Now for internal energy, when we talk about energy, there are three kinds of energy that we can consider. So potential, kinetic, and then internal. And then we already know what kinetic energy is. So energy that is related with motion in a system. Then for potential energy or gravitational potential energy, we are looking at the position of the system with reference to something, right? In this case, we are looking at it in reference to the Earth's gravitational field because all the experiments and things we are going to do are going to be done on the Earth. And then we can have internal energy. So internal energy is going to be the sum of all the microscopic forms of energy. So there would be some form of kinetic energy and then some kind of potential energy. But then we are looking at this energy between the molecules of the material that we are dealing with. So sometimes there's a little bit of even electrical energy, even magnetic energy, right? So very, very, I mean, the energies that are associated with the molecules at the microscopic level, that's what's going to constitute what we call um, internal energy. Okay, someone is asking that if saturated vapor pressure and vapor pressure are the same, then why the word saturated? So the reason why we are saying it's saturated is because remember we said if something is saturated, then we can have both the liquid, especially if you are dealing with liquids and gas, you can have both the liquid and then the gas coexisting. Or we can have the liquid being changed to a gas, then the gas being changed to a liquid. So at that point, under those conditions, we can have a system where we have our liquid and then it is forming gas, right? So if we consider even water when it is boiling, right, at a particular temperature, even water when it is boiling, there's a pressure that the vapor bubbles are coming with. But then under those conditions, it's still liquid and vapor in equilibrium. So that's why we are using the word saturated, because you can have the liquid and then the vapor together. Is that okay? Okay, so we can take it from here. So that's it for kinetic energy, gravitational energy, and then internal energy. So for internal energy, we can have some kind of kinetic energy among the molecules of a material, and then there's still some form of potential energy, that is among the molecules of what we are looking at. So all the microscopic forms of energy, when we put them together, it forms what we call our internal energy, right? And we are seeing that internal energy is related to the molecular structure and then the degree of activity. So we can look at it as a sum of the kinetic and the potential energy that the molecules are going to have. On the portion of the internal energy that is related to kinetic energy, we call it sensible energy, right? So it's just something for you to take note of. And we are seeing here that the average velocity and then the degree of activity of the molecules are proportional to the temperature of the gas. So as we increase the temperature of the gas, we would increase the amount of kinetic energy that the gas is going to have. And because we are increasing the kinetic energy the gas is going to have, then we are also going to increase the internal energy. Is that fine? And internal energy has units of joules or kilojoules because it's energy, right? And when we want it to be specific, like what we were speaking about earlier, we can divide it by the mass of the material we are working with, and we'll have it now in joules per kilogram or kilojoules per kilograms. Okay. Then we can also look at enthalpy. So enthalpy, um, okay. So enthalpy can be used for steam generation and then refrigeration. But then when we want to consider enthalpy, we want to look at the sum of the internal energy and then the product of pressure and volume. So we have that expression here where enthalpy is equal to U plus PV. And I think we came across this in physical chemistry as well. So this property, U plus PV, we put it together and we call it enthalpy. Because it's also a form of energy, we have the unit to be in joules. And when we want it to be specific, it will become joules per kilogram or kilojoules per kilogram. Okay. I think someone was asking a question. A minute. Okay, I think when he clarifies, then I'll address the question. Now, we can also have diagrams for temperature against enthalpy. So remember we looked at pressure against specific volume, temperature against specific volume, pressure against temperature. You can also have one for temperature against enthalpy, pressure against enthalpy, right? Okay, sure. So we can have all of these things. So we can have a graph of temperature against the specific enthalpy as well. And you realize that when we have a vapor, the specific enthalpy is going to be higher than when we have a liquid, right? Because if we should think about it, there should be, we can think of enthalpy in a way as the heat content that the material has. Definitely, there's going to be more enthalpy for vapors than there is going to be for liquids. Is that fine? And if we should do the same thing for internal energy, we'd have a very similar diagram because remember, we are saying that gases are going to be more energetic. They are going to have more kinetic energy than liquids. So their internal energy will also be higher than for liquids. Is that okay? Okay. Now we can talk about specific heat capacities. So we can relate these properties to internal energy and then to enthalpy as well, right? And these properties, they are specific heat capacities at constant volume or at constant pressure. And how we define them is the specific heat capacity at constant volume is just the change in the internal energy with respect to the change in temperature when we keep volume constant. The specific heat capacity at constant pressure, looking at the change in enthalpy with respect to the change in temperature when we keep pressure constant. But we can also determine these macroscopically, right, through exacting property measurements. So what we are trying to say is that maybe I can look at two different temperatures at a constant pressure, and then I can determine their enthalpy, and then find the changes, and then use that to determine what the CP is going to be. Is that okay? So these are the expressions for specific heat capacity at constant volume and then specific heat capacity at constant pressure. Now, if we want to find the internal energy or the enthalpy from these relations, what we can do is that we can make them the subjects. So if I make du the subject here, I'll have Cv times dt. If I make dH the subject here, I'll have Cp times dt. Then I can integrate both sides and it will give me the expressions we have down here. So the change in U will be Cv dt. So that's what we have down here. And if I should integrate it, it becomes this change, a finite change, right? That's what we call it. So it becomes this change. We can use this to find the change in internal energy of the material. We can do the same thing for enthalpy. So I can make the H the subject. I'll get CPdT. So that's what we have over here. And I can integrate both sides to get the actual change in the enthalpy, right? So these are properties that we can relate to internal energy and enthalpy so that we can determine their values for a given change in temperature. Okay. Now, on specific heat capacities, one thing to note is that Cp is always going to be higher than Cv, right? So the heat capacity at constant pressure is always going to be higher than the heat capacity at constant volume. When we are dealing with ideal gases, we can make some assumptions, or we can work with some expressions. So we can say that this specific heat capacity at constant pressure is just 7 over 2 times the universal gas constant, right? And that's for diatomic gases. If it's a monoatomic gas, then we use 5 over 2. If you're considering the specific heat capacity at constant volume, then these are the um, coefficients we rather use. So 5 over 2 for diatomic, and then 3 over 2 for monoatomic. But then in most cases, the specific heat capacity is dependent on temperature. It's a function of temperature. And so we can have this relation down here, right? And for this relation, we can get the values of the coefficients from tables. So the material I sent to you guys would have a table for that. Let me open it up. Should be a path for that. Okay, I think it's table 8. So good. So this is what we are looking for. So the constants you looked at. So we are saying that the specific heat capacity is a function of temperature. So there are certain constants that we can put in, right? And then we can fix in at temperatures after we do the integration. So if maybe I'm looking at nitrogen, the value for A, I'll put that in there. The value for B, I'll put that in there. The value for C, I'll put that in there. The value for D, I'll put that in there. And mind you, these constants also work in a given temperature range, right? So after we do all of that, we can um, get our expression for our Cp or our Cv, right? But then if we want to put it in an expression like this, remember it's a function of temperature. So we'll integrate it first, and then we'll put in the temperature change, and then we'll find that maybe enthalpy or a specific enthalpy, and specific internal energy or specific enthalpy. Please, is that okay? Okay, someone is asking out what is Cx. So the x is just representing either the P or the V. So we can do it for maybe Cp as constant pressure or Cv as constant volume. So the x is just representing the P or the V. And what we are saying is that usually the expression, we don't have powers that exceed 4. So usually it's just up to maybe t to the power 4. Okay. Now, remember we said our enthalpy is equal to U plus PV. When we are dealing with an ideal gas, we can say that PV is equal to RT, right? So this PV here, I can replace it with RT to get my H to be equal to U plus RT. Now, if I should differentiate the whole expression, I'll get dH to be equal to du plus RDT. The reason why it is RDT is because R is a constant, so I can just bring it out and then differentiate the temperature. And then remember from here, we said that if I make the H the subject, it's going to be CPdT. And if I make the U the subject, it's going to be CV dt. So this dH here, I can change it to CPdT. And then this du, I can make it CV dt. Now there's dt in all the terms, so I can divide through by dt. And then I'll end up with Cp is equal to Cv plus R. So that's the relation between our specific heat capacity at constant pressure and the specific heat capacity at constant volume. So Cp is equal to Cv plus our universal gas constant. And if we want it in the molar form, we can have Cp in a molar form to equal to Cv plus our universal gas constant in a molar form. Okay, I'll go over this part again, don't worry. So what we are saying is that enthalpy H is equal to U plus PV. But when we are working with an ideal gas, we can say that PV is equal to RT. So this PV expression here, I can replace it with the RT. So that we have over here. So I have H is equal to U plus RT. Then I can differentiate the whole expression. So if I should differentiate the H, I'll get the H. If I should differentiate the U, I'll get the U. If I should differentiate this term here, R is a constant, so I can keep it out. And then I'll just have dt. Now, you say that the H is the same as Cp dt, and du is the same as Cv dt. So now I have dt in all the terms. I can divide through by dt. And I'll end up with Cp is equal to Cv plus R. Right, so the difference between what we have here and what we have here is that this is in the molar form. Our units are something per mole. Is that okay? But then this is not in the molar form. So it is not per mole. Then we have another term, K. So K is just Cp divided by Cv. When we do that for air, the value is 1.4. And then for monoatomic gases, we have 1.667. Okay, so the bar on top of the Cp and the Cv is just indicating that it's in the molar form. So whenever you see a property with a bar on top, we are saying that it's in a molar form. So it is something per mole. Is that okay? So if I have okay, remember, if I have capital H, this is going to be enthalpy. If I have small h, it's going to be specific enthalpy. So it is this divided by mass. But then if I have my small h with a bar on top, then it's still specific enthalpy, but then it is now divided by moles instead, not mass. Is that okay? So just take note of that notation. Everything with a bar on top is in a molar form, so it is per moles. Okay. Now, the substances that we would be working with a lot in thermodynamics, water, that's one of the most common materials we work with because we use it for heating, we use it for cooling, and it's the main fluid that we use in most power plants. Then we have gases. So we use them similarly to water. So we can use them for heating, we can use them for cooling, we can use them for expansion, compression, a whole lot of things. Then we have refrigerants as well. So these are liquids that are very volatile. They can easily become vapor. We use them in refrigerators, use them in air conditioners, use them in heat pumps. So we'd see them, would have questions on them, and we'll see how they are used as well. Then we have what we call reference states. Now, this part is also very important. So the thing about reference states is that when we are measuring properties like enthalpy, internal energy, entropy, these things are not properties that we can easily measure. So what we usually look for is rather a change in enthalpy or a change in internal energy or a change in entropy. So because we are looking at a change, then we need something that is going to act as a reference or as a baseline or as a starting point. So let me give a little example. Let's say you have some amount of money, but you're not sure of the exact amount. So maybe you have some money, maybe in your bank account, you have some physical cash, you have some money in your mobile money, but you don't know what the actual amount is. You don't know what the total amount is. And then somebody's about to give you some amount of money. For you to be able to determine the actual money you have, you won't be able to do that at that point. But then you can tell that the amount of money you had increased by something. So that's what we are looking at. So the reference state is where you are now. You are taking it as point zero. So you say that maybe my amount of money increased by 50 cedis, but then you know that the amount of money you have is not 50 cedis. So we are just measuring the change. Usually that's what we look at. So when we talk about the reference states, we are saying that we are taking something to be a baseline. At this point, we are assuming that the value is zero. So if at this point the value is zero, and I should have 50 being added, then it means that the amount by which it has increased is 50. So that's what we are just trying to see. So what we do is that for thermodynamic properties, we can get our data from certain tables or certain materials, but then they are going to be at certain references. So at one point, you might look at the enthalpy at a particular temperature and pressure. That value you see, it doesn't mean that that is the actual enthalpy of the system. It means compared to a particular condition, the enthalpy is going to be this. Is that okay? So we are looking at the change. Is that okay? So we are assuming that our reference is going to be 0. So I think there's an example here. For water, the state of saturated liquid at 0.01 degrees Celsius is taken as a reference state. Because we are taking it as a reference state, it means that we are assuming that the properties there are all 0. So we are taking internal energy there to be 0. We are taking entropy there to be 0. So every property, like internal energy and entropy, we are assuming them to be 0. So that's going to be our reference. So every other temperature we get, what we read is just going to be a change in the enthalpy, entropy, internal energy. Is that okay? And the thing about reference states is that you might have one material that is using one reference state, another material that is using another reference state. So you see different values. So what we have to do is that you have to be consistent in the particular table or the particular chart you are working with. So if you are working with table A, work with table A throughout. If you should go and pick data from another table, you might end up having a wrong answer because they might be using a different reference state. Is that okay? Please, is that okay? Okay, and that's good. Okay, someone says not quite. So what we are saying about the reference state is that um at certain conditions, right, we are taking properties like internal energy and entropy to be 0. So for water, we are taking it that at 0.01 degrees Celsius, when it is saturated, the enthalpy, the internal energy, the entropy, they are going to be 0. So if I should increase the temperature, the value I'm going to get is relative to that initial point that we are considering, that reference point we are considering. Another table might see that, okay, instead of 0.01 degrees Celsius, we would use maybe 0.05 as a reference state. So when they increase the temperature, their values will be a bit different. So the various tables and charts we have, they are all based on a certain reference state. They take one condition and then they assume that under those conditions, the values are going to be 0. So what we are saying is that when you have data you are supposed to read from a table or from a chart, you need to ensure that you are consistent with your reading. You don't read from one table and then pick values from another table and then try to put the two of them together and solving a question. Is that okay? Because they are all taking their starting points from different places. Is that okay? Okay. So there are various sources where we can get thermodynamic data from. So we have thermodynamic tables, like the material I sent to you guys. Oh no, the tables are given to you during the examination. You can't memorize. You can't. They are not things you are supposed to memorize. No, no, no. The tables will be given to you. If there's um thermodynamic data you have to read from a table, you would have the tables. So I've actually sent you the tables. I sent them I think on Sunday, right? So you can reference them. So we have thermodynamic tables. So we have steam tables, we have tables for air and different things. And we have different kinds of charts. And then we can also have relations. So sometimes instead of maybe picking your data from tables and charts, you can have an expression that if you put in maybe certain conditions, temperature, pressure, specific volume, it can give you what you are looking for. So we call these relations, these relations, an example is our equations of states. So we'll come to that very soon. And another place we can get data from our computer software. So there are some software that have the data embedded into their database. So we can access the thermodynamic data from them. Okay. So now let's look at equations of states. When we say equation of states, we're looking at an equation that is just relating pressure, temperature, and a specific volume, right? So we can express them in a pressure form or in a volume form. What we mean by that is we can look at it as pressure as a function of temperature and then the specific volume, or we can look at the volume as a function of temperature and pressure, right? And then the most common equation that would fit this is the ideal gas equation. So we know that PV is equal to nRT. In that case, we are saying I can make P the subject. If I make P the subject, then now pressure is a function of the temperature and the volume. Or I can make V the subject. If I make V the subject, now volume is a function of temperature and pressure. So that's what we are just trying to see from here. So we have the ideal gas equation, PV is equal to RT. So P is our pressure, V is a specific volume, T is absolute temperature, and then R is our gas constant in kilojoule per kilogram Kelvin. So please take notes of this very well, okay? For us, when we use R, we are saying kilojoule per kilogram Kelvin. When we use RU, then we are saying kilojoule per kilomole Kelvin, right? And then the relation is that R is equal to RU divided by the molecular weight of the gas we are dealing with, or the mixture of the gases we are dealing with. So if I have kilojoule per kilomole Kelvin, and I divide by the molecular weight, which is kilogram per kilomole, I'll end up with kilojoule per kilogram Kelvin. Is that okay? Is that okay? Okay. Now we also know that PV is equal to nRT. So this R is the R we know, the kilojoule per kilomole Kelvin. If we should divide through by N, right? If we should divide both the left and the right sides by N, what we are going to get is V over N. So that's the specific volume on a molar basis. So remember we said everything with a bar on top of it is per mole. So now I'm dividing this V by the number of moles. So now I'm going to have my specific volume, but then in terms of moles. So it's going to be maybe meter cube per mole. Is that okay? And then I'll have here RUT. Is that fine? Okay, that's good. There was a question I was expecting someone to ask, but I think I'll give it to us as an assignment. It will be a proof question. So I'll send it to the page. Okay. So when we continue looking at the ideal gas equation, right, we are dealing with the ideal gas based on, okay, someone has asked the question. So someone says I should go over the formula. Yes, dividing by moles also makes it specific. Yes, when we divide by moles, it also makes it specific. I think we've said that a number of times. Now, someone is asking why there is no N up here. So that's what I wanted you guys to go and prove, right? So you start with this relation here, and you work with what we've spoken about here. So I'm just giving you a hint. You start with this relation here. You work with what we've done over here, right? And when you should solve it, you end up getting this expression here. So I want you guys to try it out. Yes, someone has asked. So I want you guys to try it out, and then would send you the actual solution. I mean, we'll send the final solution to the page so you can compare your answers. Okay. So please let's try it out by the close of today. Okay. Sure. Oh no, it's still an assignment. It's still an assignment. So you guys should try it out. Okay. So for the ideal gas equation, we are working based on certain assumptions. Um, I should come again with the questions. Um, Amanda, can you please explain? I don't get what you are saying. Oh, I'll send it to the page, so don't worry. I'll send it to the page so you'll get it from there. Okay. So the ideal gas equation, we are working based on certain assumptions. And these are things we are also very familiar with, right? So we're assuming that the gas molecules are small and that the sum of the volume of the individual gas molecules is negligible compared to the volume of the container. We're also assuming that there's going to be um, elastic collision between the molecules, right? And then we're also saying that except during the collision, the interactions among the molecules are negligible. So they are not going to exert any force on each other. So we are very familiar with these things. Usually these conditions happen when we have very high temperatures or very low pressures. So these conditions would allow for our gas to behave like an ideal gas, high temperatures and then low pressures. Is that okay? But then the thing is that most of the time, we may end up dealing with real gases. So there has to be a way that we can correct for the deviation in the behavior. If we assume the gas is ideal and then we are actually dealing with a real gas, realize that what we determine in terms of the properties would deviate from the actual properties of the gas. So in order to cater for the deviation, we need to also have equations of states, or we need to have correction factors that would allow us to relate the ideal to the real, right? So we might have correction factors that will help us relate the ideal to the real, or would have certain expressions that we can use for just real gases. Okay, so we are saying that at high pressures and low temperatures, the behaviors of the gas will deviate from that which is prescribed by the ideal gas equation. So now there's actually an intermolecular force between the molecules, and then the collision is not going to be perfectly elastic. Then the volume of the gases too are also significant. So we need to have equations that would account for these deviations. So some of the things we can do, we can work with the compressibility factor. You can work with the Varroa equations. We can work with the cubic equations of states. So for the compressibility factor, it's not something that's new to us. Note that the compressibility factor is just a correction factor. So that Z term, right? We are going to relate it to the volume of the actual gas or the real gas divided by the specific volume of the ideal gas. So if I make V actual the subject, it's just V ideal times Z. So Z is going to, in quotes, modify V ideal to give us the actual V, right? So we can say that PV is equal to ZRT. So this Z here, if we should put V actual over V ideal in here, right, then it means we are going to make it give us the properties for the real gas that we are considering. Is that okay? Please, is that okay? Um, in a way, yes, yes, yes. In Anakwame, yes. It will be for the specific volume. Okay, so what we are saying is that the compressibility factor is just a correction factor, right? So we know that PV being equal to RT would have been the case for the ideal gas, right? So if I have PV is equal to RT, it's going to be for the ideal gas. Now, if I should multiply it by Z, then I'm correcting the deviation from the ideal gas so that I can get the actual properties for the real gas. So that's all we are just trying to see. Is that okay? Benjamin, is that fine? See, but with PV is equal to HRT, we can still incorporate the most. Yes, you can. So remember we said we can have the expression in this form. If you're working with it in this form, it will be PV is equal to ZNRUT, right? So we are working with this form where the V here is specific but with respect to mass. So it's meter cube per kilogram. We are working with this expression here. So that's why we just use PV is equal to ZRT. But then we can use this one as well and make it PV is equal to ZNRUT. Is that fine? Okay, so then we can move on. So for the compressibility factor, we know that if you want to find the compressibility factor, it's going to be a function of the reduced pressure and the reduced temperature. Sorry, there's a question. So please, specific volume means we are considering one more. Um, you can look at it that way. But then realize that it's not only just for moles, it can also be for mass. So you're saying that maybe for 1 mole of a material, what is the volume going to be? Or for 1 kilogram of a material, what's the volume going to be? So you can look at specific volume in that term here. Is that okay? Okay. So for the compressibility factor, the Z, right, we are saying that it's a function of reduced pressure and reduced temperature. And this is based on the principle of corresponding states, where it says that um, gases at the same reduced temperature and the same reduced pressure behave the same way. So if I have a gas, maybe gas A, and it has a particular reduced temperature and pressure, and I have gas B, it has the same reduced temperature and pressure, their Z factor would be literally the same. So that's based on the principle of corresponding states. And this works for usually for certain materials, not all materials, or for simple um things. We'll come to that as we move on, right? So all we are trying to say is that our compressibility factor, the Z we are looking at, that correction term, is a function of reduced pressure and reduced temperature. And for the reduced pressure, it's just the pressure that the system is at divided by the critical pressure of the material. And for the reduced temperature, it's the temperature that the system is at divided by the critical temperature of the material, right? And then we have charts that we can use. So if I should have my reduced pressure, maybe I found my value for my reduced pressure, I can trace it to this curve to where I have my reduced temperature and then read the corresponding Z. So let's say I calculate and find my reduced pressure to be 3.5, right? So I can draw that line up here. And I'm looking at a reduced temperature of maybe 1.1. So that's going to be this curve here. So where they intersect, I can just extend it to the y-axis and I'll have maybe 0.52 to be my Z. Is that okay? So that's how we make use of the compressibility charts as well. Okay. So for the critical temperatures, critical pressures, and even the critical Z factor, there are also tables for them. Okay, someone says I should go over the graph. So what we are saying is that to find our Z, it's a function of reduced pressure and reduced temperature, right? So if Z is going to be a function of reduced pressure and reduced temperature, it means I have to first find my reduced pressure and then find my reduced temperature. To find the reduced pressure, it's P over PC. That's the critical pressure. Sorry. And then to find the reduced temperature, it's T over TC. That's the critical temperature. So I can find both of them. So what I'm saying is, if maybe we found those values and then I had my reduced pressure, that's down here to be 3.5. I can just draw a line at the 3.5 points. And then I can look at my reduced temperatures as well. So realize that the curves are all labeled. So this one here is for the reduced temperature of 1. This one here is for reduced temperature of 1.1. This one here is for reduced temperature of 1.2. Right. So let's say I'm dealing with, okay, someone says they don't understand reduced. Okay, I'll talk about it. So let's say we choose a reduced temperature of 1.2. So where that 3.5 line meets the 1.2 curve, we can trace it to the y-axis and then read the z. We are calling it reduced because we are comparing it to something. So we are not working with the actual pressure of the system or the actual temperature of the system, but we are comparing it relative to its critical pressure and its critical temperature, right? So when we see something is reduced, we're just saying that it is the property divided by its its critical property, especially for temperature and pressure. Is that okay? For volume, there's a little relation there, but then for pressure, for temperature, it's just the pressure and the temperature divided by the critical pressure and then the critical temperature. Is that okay? Okay, we can move on then. So I was saying that we can read our critical temperature and pressure of various substances from different tables as well. Okay. Now we can come to the Barrel equation. So what we are saying here is that if we should consider the ideal gas equation, PV is equal to RT, as the product of pressure and the specific volume, usually at constant temperature, should be constant. So let's say I have PV is equal to RT, and I'm keeping temperature constant. We already know that R is a constant. So expecting that PV is going to be constant. And then it gets to a point where when the pressure becomes very high, when we said when the pressure is high, it is no longer ideal. When the pressure becomes very high, we are no longer going to see it behaving like a constant. So if we should look at the diagram over here, realize that it starts out at the very low pressure. So this is pressure, and then this is PV. At very low pressures, it starts out a bit straight, and then it now begins to curve. So it has a very slight curve, and then it now becomes steep, or it now becomes yes, it becomes more steep. Right. So when it happens this way, it's because the pressure is increasing and is deviating from the ideal gas behavior. Okay. So what happens is that now it begins to assume a polynomial kind of relationship, a polynomial nature. When we say it's polynomial, it's because there's going to be some kind of curve or some kind of turning point at a point. Right. So that's why it's looking like a polynomial expression. So now instead of we saying that PV is just going to be equal to RT, which was going to be our constant term, we are going to have it in a polynomial form. So now we'll have maybe K1 to be the constant, then K2 times P, because it is dependent on pressure. It's a function of pressure. Then K3 times P squared, K4 times P cubed, and we just keep going, right? So that's how polynomial expressions look like. I think we are fine with how polynomial expressions look like. So, I mean, from math 152, I'm sure you came across that, yes, in calculus. So from how polynomial expressions look like, so we can write PV as a polynomial expression now as a function of pressure. So it's depending on P. That's why we have the P squared and the P cubed. Then what we can do is that we can factorize K1. That's the constant. So I can divide everything here by K1. When I do that, I get this expression here, right? So now the B prime is just K2 over K1. C prime is just K3 over K1. D prime is K4 over K1. And we are seeing that K1 is going to be our RT, that constant expression we're looking at. So I can just replace the K1 here with RT and then get this expression over here, right? And we can now say that PV over RT, which we said is equal to Z, can now be equal to the rest of the expression. And then we can also now put in the expression for P as V over RT into this expression here. And then we can simplify it to get what we have down here. So what we'll do is that we can write out the proof step by step and then send that one as well to you. But then these are the expressions we use. One thing about these relations is that usually we end it at the second term because it can help us get very accurate values. So sometimes we don't even consider the C and the D parts. We can just work with just up to the B part. So if we come here, I'm saying that these are known as the Varroa coefficients. And we already said that B prime is B over RT. So we can determine them from experiments, or we can determine them from theory, right? And we are saying that we can represent these equations with a wider range by including more terms, right? So we can include more terms if we want to. And but these ones are applicable for the gas phase of substances only. They don't work well for liquids or liquid vapor mixtures. So when we are dealing with these equations, we use them when we are dealing with gas phase. Okay, I'll go back to the previous slide. Yes, and when we are dealing with modules, you might have to use a software. Someone is asking what's the K1, K2, K3 are. So they are just representing constants or coefficients, right? That we can determine. Right? I don't think it's defined from say constants. They are coefficients that we can determine. So usually they are dependent on temperature, right? They are functions of temperature. So they are just going to form part of the expression. Remember, we said we are keeping temperature constant. At a particular temperature, we can get a certain K2 value, we can get certain K3 value. There are expressions for them. So we just plug in our temperature, we can get those expressions, right? And then someone also said, um, okay, they were lost on this slide. So what we are saying is that when we are looking at PV, from the ideal gas equation, PV is equal to RT, right? If we are keeping T constant, we are expecting R to be kept constant because R is a constant. So it means that PV is equal to a constant. So it's a constant itself. So we are expecting that for a particular temperature, PV is always going to be constant. But then the issue is that when we increase the pressure to a certain point, it no longer behaves constant. The graph starts to curve. When the graph curves, it's because it has a polynomial kind of nature. So we can represent PV in a polynomial form. So that's the expression we have here. And all that they are doing is that they are just factorizing K1 out. So we are going to divide everything by K1. So K2 over K1 is what gives the B prime. K3 over K1 is what gives the C prime, right? We'll write it out and then we'll send it to you. But then that's what's just happening here. So we can replace this K1 now with RT because that was the constants we're considering for the ideal gas equation part, right? So we can make PV over RT the subject. That'll give us Z. Then that will become 1 plus the rest of the expression we have down here. Can also simplify it further by replacing the P terms here. And then we can get the Z expression down here as well. So usually this is what we work with. Is that okay? So yes, please note, we use these ones for gas phases. We don't use them for liquids or liquid vapor mixtures. Okay, sure. Another thing we can, okay, before we get there. So we are saying that the second coefficient, that's the B prime. You can obtain it by using this relation. So this is what we are doing. See this expression we had here for the Z as a function of pressure. If I should differentiate the expression with respect to pressure, right? Hello, can I be here? Okay. So I think the network point's a bit unstable. So what we are saying is that if I should take this expression and differentiate with respect to pressure, right? I'll have maybe dz dp. This is a constant, so it goes away. I'll have just b prime. I'll have 2 c prime p. I'll have 3 d prime p squared. So that's what we are just doing. So they just differentiated it with respect to pressure, right? And they're looking at what happens when pressure goes to zero. So if the pressure is going to zero, this term goes away because pressure is going to zero. This term goes away because pressure there is going to zero. So I'll just be left with the dz dp to be equal to my b prime, right? So if we want to end the variable equation of state at the second term, we can just have 1 plus bp, b prime p, and we can find that value of b prime p by differentiating the expression, sending p to 0, then we can get that value, right? Or we can just truncate at the second term and have 1 plus b over v. So that's what we have over here. And we can relate it to PV. And then we can make P the subject. We'll get this expression as well, right? So one of the references that we sent you, they propose that for non-polar fluids, the expression for B can be written as this. So we have our gas constants, we have our critical temperature and pressure. Then we have this B naught term. So that one is also expressed here. Then we have the B1 terms also expressed here. And then we have this omega symbol. So this symbol is what we call the eccentric factor. It might look a lot, but then when you go through, you realize that it's actually understandable. And as you solve more questions, it will be fine, right? So this omega symbol here is what we call the eccentric factor. Okay. So please, can we go on? Okay. Start from as p approaches zero. Okay. So what we are saying is that when we differentiate, we have this expression. When p is approaching zero, we can see that this value here, let's say this p is going to zero. This whole term here, the 2c prime p becomes zero. If p is going to zero, this expression here, the 3d prime p squared will also go zero. Because imagine I'm just putting zero here. The whole expression goes to zero. So when p is approaching zero, this whole term, the dz dp as constant temperature, is just going to be left with the b prime because all the other terms go to zero. So we can use that to determine the value of the b prime, right? Then for the equation of states, if we are ending it at the second term, so that's this relation we had here. If you're ending it at the second term, this is the first term, this is the second term. So we are ignoring everything else. Or we can have it in this form. So one is the first term, b over v is the second term. We can ignore everything else. So if we should do that, we can have z to be equal to 1 plus b over v. Then we can relate it to, remember we said z was pv over rt. So you can relate it to pv over rt and make p the subject. And we can get this. What we're also saying was that there's a reference that we sent to you. So they were saying that for non-polar fluids, we can have this expression for our B. So this is the expression we have, and then they've defined the various terms they have, the B0 and then the B1. But then the omega symbol here is the eccentric factor. So that's what we are about to talk about now. Okay. So for the eccentric factor, remember for the theory of corresponding states, we're saying that if we have different materials at the same reduced temperature and the same reduced pressure, then they behave the same way. So TR is a reduced temperature. TR is a reduced temperature. So they behave the same way. So they will end up having the same compressibility factor because they're going to deviate from ideal gas by the same amount. But when we have complex fluids, they don't obey this theory. So aside just using the critical temperature and pressure to find maybe your reduced temperature and pressure and find your Z, you will need another term, which is the eccentric factor, right? So for the eccentric factor, please just really pay attention here, okay? For the eccentric factor, the way they came about it was that they plotted or they found the saturation pressure of the substance, divided it by its critical pressure, and then found log of that. That's the first thing. And they also found a reduced temperature and found 1 over that. So now when you plot this, the log 10 P sat over PC against 1 over TR, okay, against 1 over TR, you get a particular graph. And then on the graph, at the point where 1 over TR is 0.7, you realize that for simple fluids, you are going to have this value on the y-axis to be -1, right? But then when it becomes a complex fluid, it deviates a bit. So now we can find the difference between the simple fluid and the complex fluid. That's the deviation that we are going to consider. Is that okay? Um, so for complex fluids, these are fluids that are going to have um some kind of interactions that make them really deviate from ideal behavior. So the kind of interactions between the molecules are in such a way that there's going to be a great deviation from ideal behavior. Yes, they are real. They will be real. Is that okay? Okay, I'll go over it. So what we are saying for the centric factor is that we can have the saturation pressure of a substance, right, at a particular temperature. And then there are lots of questions that are coming up. Okay, I'll address all of you. But we can have the saturation pressure of a particular substance at a given temperature, and then divide this by its critical pressure. Then we can find log of that. So those become our y-axis values. Then we can also find the reduced temperature, right? And then we can find 1 over that. So we can plot the log 10 P sat over PC against the 1 over TR. I'm coming. Okay. So what we are saying is that for simple fluids, usually these are fluids that have maybe just one material, maybe it's like just pure water. There are no complex interactions with the molecules. When we find the 1 over TR at 0.7, log 10 P sat over PC was always going to be -1 or very close to it. Realize that this worked for simple fluids. So in the case where you have a complex fluid, then there's a deviation from that. So it's no longer going to be -1, right? So what they are doing is that the eccentric factor is a deviation of the complex fluid from a simple fluid. So they will have the value for the simple fluid, which was -1, then minus the value that they will read for the complex fluid. So when they do this, it gives them what they call the eccentric factor. But then, I mean, you wouldn't be asked to plot this and find all of these things. Usually, the eccentric factor, we can read them from tables as well. So the values are in tables. You can find the eccentric factor for water, eccentric factor for maybe ethanol, for different materials, right? But then if you have a simple fluid, the eccentric factor is 0. Is that okay? Okay. Now we can also look at the cubic equations of states. So these are also equations of state, but then the thing about them is that they are expressing the molar volume expression, the V term in all our expressions as a cubic function or in a cubic form. So they are relating maybe pressure, temperature to the volume in a cubic form, right? And the advantage of this is that they are applicable over a wide range of pressures and temperatures. So remember for the critical, so when we're doing the compressibility factor, you said that the critical pressure and temperature are limited to a particular temperature range, right? So there are some limitations to those ones, but then for the cubic equations of states, they can be applied to a larger range of temperatures and pressures. And unlike the Barral equation of states where we couldn't use them for liquid phases, we can use the cubic equations of states for liquid phases and then for vapor phases as well. So that's one very good advantage of the cubic equations of states. We can also extend them to mixtures, so we can consider mixtures as well. So maybe a mixture of two different materials, we can still use the cubic equation of states to determine our properties, right? So the first cubic equation of states that we are going to consider that was formulated was the Van der Waal equation. And that's what we have here. So we are very familiar with this, right? Someone says it has changed. Okay. So that's the Van der Waal equation. I think maybe the form you are familiar with is this. I'm sure this is the form you are familiar with. Okay. It's just change of subjects, but that's the Van der Waal equation, right? And for the Van der Waal equation, remember we are saying that it's going to consider real gases. So it's going to account for the deviations that are happening from ideal to real. So this A over the V squared term here is going to account for the intermolecular forces of attraction, right? And then the volume that's being occupied by the gas molecules. Remember for the real, so for ideal gases, we are assuming the volume is negligible, but for real gas, there's actually a volume. So the volume that will be occupied by the gas molecules is going to be that B term. So we put it in there. So when we have it, it's now going to be um, something we can use to model real gases. Then this A expression, we can express it this way, or we can read it from tables. The same for the B, we can express it this way, or we can read it from tables, right? So for the Van der Waal equation, the total pressure that we are looking at is going to be the attractive pressure and then the repulsive pressure when we put them together, right? And for the repulsive pressure, it's going to be expressed with RT over V minus V because it's supposed to be the term that is dependent on temperature. The reason is that if I increase the temperature, I increase the amount of repulsion between the molecules. So the repulsive pressure is equal to RT over V minus B. But then when we are looking at the attractive pressure, it's going to be the other term we have. So that's going to be the A over the V squared. So what we are saying is that the total pressure in the system is equal to this. So this is the repulsive part. Then this is the attractive part. The negative is coming in because they are opposite to each other. Is that okay? So the repulsive pressure, we are saying that when the volume um, of the gas is approaching the volume of the system, then we are going to have that pressure approaching infinity, because if V and B are close to each other, then it means that the denominator is going to go to zero. And anything over zero gets very large, it gets very close to infinity, right? So it means that we are going to expect an infinite repulsive pressure. And then in the case where we have the volume of the um, system increasing, so that's for the attractive point. When the volume of the system is rather increasing, what's going to happen is that the attractive pressure would reduce. Is that okay? Because now we are making the denominator here larger. So the overall expression will be smaller. If we divide something by a larger value, it becomes smaller. Is that okay? So that's all we are just trying to say from this page. So here we're saying that while the Van der Waals equation is no longer in common use, it has proved to be a useful foundation for equations of states. So there are other equations that were formulated, and they were based on the Van der Waals equation of states, or they look similar to the Van der Waals equation of states. They are just a little modifications that were done. Some of them are the Penn-Robinson and then the Suave-Redlich-Kwong. So usually we shorten it to SRK, the SRK equation. So this is a general form. Sorry. So this is the general form of those equations of states. And then these are the specific forms for the SRK equation and then the Peg-Robinson equation. Right? So all we are saying from the general form is that if I should make RUT the subject here, just as RUT was made the subject here, I'll get an expression. So P plus all of this, right, multiplied by V minus B. Now, all these terms can be certain constants, or they can represent maybe the A and the B terms here, right? So there are just a lot of different modifications. They put in values for all these constant terms we are seeing, and then they get another equation of states that they can work with. So this was just a general form. And then these guys, Suave-Redlich, Kwong, and Penn-Robinson, just found certain constants that would make the equation more accurate. And then they formulated their equations down here, right? So, I mean, these equations, you would familiarize yourself with them as time goes on. Okay, the screen is frozen. Okay. Now, we spoke about the fact that when we are considering maybe deviation from real to ideal, we can use compressibility factors, we can use the Van der Waals equation, we can use equations of states, right? So that's what we've just looked at. And now we want to look at places we can also get properties from, if you're not even maybe considering these equations, right? So we can get properties of thermodynamic systems from tables, and we send the material to you once again, so we can easily reference it, right? So these properties are usually presented in the form of tables. Some of them we can measure easily, some we can't measure easily. So the ones we can't easily measure, we can always go to a table for confirmation. And then the most common of these tables is the steam table. So you really, really make use of the steam table. Like in CPC2, you make use of the steam table. So get familiar with the steam table. Let it be your friend. And then there are tables for other materials as well. So we have tables for air, we have tables for nitrogen, for oxygen, for carbon dioxide, for refrigerants, things that we use for cooling, all these things. So we have tables for all of them. So let's look at the tables. I would pick just one. So this is the material we sent you guys. It's about 50 pages. And if we should pick, so this is for water, right? So what we call the steam table. So what we are saying is that if I have a particular pressure, I can determine the temperature at which it will be saturated. And then from there, I can determine different properties. So I can determine its specific volume for the liquid and then the vapor. I can determine its internal energy. I can determine its enthalpy. I can determine its entropy. So, right. So instead of we having to use equations and model it, we can pick the data from the table, right? You can have tables for other materials as well. So this is for refrigerant 134A. So at a particular temperature and pressure, I can determine its properties. We have tables for air as well. So we have tables for um sorry. So we have tables for air. So we can tell maybe the enthalpy at a particular temperature of air. We can tell the reduced pressure at a particular um temperature for air. And we can even have for specific components of air. So maybe for nitrogen, for oxygen, for carbon dioxide, right? So we have these different tables that we'll be making use of in the course of the lesson. Okay, so that's it for the property tables. So we said that we can have steam tables. And for the steam tables, we can use it to determine specific volume, internal energy, enthalpy, and entropy at different conditions of temperature and pressure, right? So I think we've already looked at the steam table. So we've already seen how it looks like and how we use it. For the steam table, okay, I think that's fine. We've spoken about it. So for the steam table, these are some of the things we can do with them. So we can say maybe we want to find a specific volume of the saturated vapor at 30 degrees Celsius. So we'll try that one out, right? Let me change the screen. So a specific volume at 30 degrees Celsius. So we'll go to the steam table, the one that is for steam. Okay, so that's what we have here. So this is for steam, so saturated water. So that's going to be the steam table. And now we're looking at 30 degrees Celsius. So this is 30 degrees Celsius here. So notice there's temperature here, right? So this 30 degrees Celsius. So the specific volume, we have that of the vapor, and then we have that of the liquid. So we can read the specific volume and then take notes of the units, please. Please take notes of the units, right? So we can just read that one, and then we are done with it. So the specific volume of the saturated vapor. So we read the one for the vapor. Then the next one says the vapor pressure of steam at 55 degrees Celsius. So if I'm looking at 55 degrees Celsius, that's here. So the vapor pressure there is going to be this value here. That's the saturation pressure. So that's 15.763 kilopascal. So you're basically just finding the points you have and then relating it to the other properties on the table to determine them, right? So that's all we do with the tables. That's how we work with the tables. One thing to also notice is that sometimes the tables they can work based on temperature or based on pressure. So realize over here that at the far left here, we have the temperatures and then we are given their corresponding saturation pressures. Sometimes you might have a point where you're rather given the pressure and then you have the corresponding saturation temperature. But then they'll always give you, if you look at similar points, you always get the same values. Is that okay? If I pick maybe a particular temperature and then work with a particular pressure here, right? It will be the same thing if I pick a particular pressure and then work with its corresponding temperature as well. Is that fine? Okay. So we'll try out these others as an assignment as well, right? Okay. So now we'll talk about the quality of steam. So for the assignment, this is one. Then the proof question is also one. And then I'll also send you one where you determine the phase of the materials and under different conditions, right? So now let's talk about steam quality. When we are okay, sorry about that. Let me share the screen again. When we are vaporizing a material, there's a part of the material that um is liquid and there's a part of the material that can be vapor. Right? So we can have the liquid and then the vapor existing together. So what we want to do is that we want to be able to determine the fraction of the liquid and then the fraction of the vapor in the entire mixture of the liquid and then of the vapor. So if I have maybe the mass of my vapor, divided by the mass of the mixture, then that gives what we call the steam quality, right? So if the steam quality is 1, it means that all of what I have is just vapor. So the mass of the vapor is equal to the mass of the system. If the steam quality is 0, it means that everything I have is liquid. So the mass of the vapor is 0. 0 over m will give me 0. So the whole thing about the steam quality is that we use it to determine how much vapor or the fraction of vapor we have in a liquid vapor mixture. Is that okay? So that property or that quality, we call it steam quality. So it's the mass of the vapor over the mass of the entire system. Now, for the steam quality, we can prove it or we can find it from relations like this. So this is the specific volume. What we're saying is that, oh, so there was something I forgot to mention. When we see VF or anything with a subscript F, it is talking about the liquid components of what we are working with. When we see VG or anything with the subscript G, it's talking about the gas or the vapor components of what we are dealing with, right? So VF is just the specific volume of the um the liquid part or the water in the water steam mixture, right? Or the liquid vapor mixture. It's just the liquid part. And then VG is the specific volume of the vapor part of that mixture. Is that okay? So what we are saying is that V, that's the total specific volume, is equal to VF plus X VG by net VF. So this is the relation we are coming to prove. So we know that the total volume of a system is going to be the volume of the liquid plus the volume of the gas. So this is total volume. But we also know that the total volume is equal to the mass times the specific volume. So this specific volume is the specific total volume. And we said that if it is specific, it is divided by mass. So if I want it to be extensive, I don't want it to be specific anymore. I can multiply it by mass so that I get my big V. So I can replace this big V here with MV. And then the VF here, I can also replace it with MF times VF. So that's the specific volume of the liquid multiplied by the mass of the liquid. Then I have the specific volume of the gas multiplied by the mass of the gas. So when I do that, I can add all of them. I can place them into this expression, right? And then I'll get, um, yes, I'll get this expression over here. And then we also know that the mass of the entire mixture is the same as the mass of the liquid plus the mass of the gas. So I can just make MF the subject here. I can just make MF the subject here and then put that into this expression. When I do that and I make V the subject, I'll get this expression over here, right? Someone says I should take the previous sign again. Okay. I'll go over it again. So what we are saying is that we have what we call the quality of steam. The quality of steam is just talking about the fraction of the steam liquid mixture, right? That is going to be vapor. So it's like if we are heating water and it starts to vaporize, there's some amount of it that can remain liquid, there's some amount of it that remains as a vapor, right? We want to find the fraction of the vapor related to the total um, mass of the system. So we want to find out how much vapor is there compared to the entire mixture, a mixture of both liquid and vapor. So that gives us what we call the steam quality. So the steam quality is just the mass of the vapor divided by the mass of the entire mixture. And then there's a proof we want to do. So we are saying here that this term here is what we call the specific volume for the mixture. The VF is the specific volume for just the liquid part of the mixture. And then VG is the specific volume for just the gas part of the mixture. So what we are saying is, if I'm looking at the volumes, now not specific volumes, just the volumes, right? So the volume is going to be the volume of the liquid plus the volume of the gas. So that's what we are saying. The volume of the mixture is the volume of the liquid plus the volume of the gas. But we also know that the volume of the mixture is going to equal to the mass of the mixture times the specific volume of the mixture. And it is coming from, yes, liquid is F. Yes. When we say fluid, fluid can be liquid or gas. But then if it helps you remember, you can take it that the fluid is representing a liquid. But yes, the subscript F is for liquid, subscript G is for gas. So what we are saying is that here, let me write that one. You know that if I have my volume and I divide by my mass, it will give me my specific volume. So that's going to give me my specific, so that's my lowercase v. So they just made the big V the subject in this expression over here, right? So that the big V becomes M times V. So that big V here, we replace it with that M times V. So that's what gives us this. And we do the same thing for both the liquid and then the vapor volumes. So the volume of the liquid is going to be the mass of the liquid times the specific volume of the liquid. And then the same thing for the vapor. So the volume of the vapor is going to be the mass of the vapor times the specific volume of the vapor. But we also know that the mass of the entire system is going to be the mass of the liquid plus the mass of the vapor. So if I should make the mass of the liquid the subject, right, I'll have MF to be equal to M minus mg. So that's the expression that we have down here. So I can replace this MF here over here with the M minus the mg. Are we okay with that so far? Are we okay up to that point? Good. So now if I replace the MF here with M minus mg and I make V the subject, this MF is going to become M minus mg. So that's what we see here, right? Times this VF. Then we have mg times VG. That's what we see here. Then we are making this V the subject, so I can divide through by the mass. So that's why we have the mass dividing everything. Then we said that X, that's the steam quality, is the mass of the vapor divided by the total mass. So if I should divide the terms individually, this mg over m here becomes X. So that's giving us the XVG. The mg over the m here becomes X. So that's giving us the minus XVF. And then m over m becomes 1. So that's giving us just the VF. Right? Then we can factorize VF out. When we factorize VF out, we end up with this expression now. Is that okay? Or we can even factorize X and then end up with this expression instead. Right? So that's it. So that's the expression. And we can apply it to other properties. So we can do the same thing for enthalpy, internal energy, and entropy. So all we are saying is that if you want to find the enthalpy of a material, you can take the enthalpy of the liquid, the enthalpy of the gas. When you know the steam quality, you can put all of them into the expression and get the enthalpy of the mixture. So someone is asking that, can we also make mg the subject and substitute? The problem with that is you can do it and end up with the same answer, but then you struggle because if you make mg rather the subject, you're going to get m minus mf, right? But then if you do that, you end up having m minus mf here divided by m. But then the x is mg over m, not mf over m. So if you make mg the subject, you rather end up having mf staying in the expression, and it makes it more complicated. So you can actually work it out from there, but then it will be a longer procedure. So it's safer to work it out from this point where you rather make MF the subject. Okay. So what I was saying was that if you know the enthalpy or internal energy or entropy of the fluid and that of the gas, and you know the steam quality, you can put them in this expression and then get the enthalpy of the mixture. So sometimes you might be given a question that says that maybe you have a steam quality of 0.7, right? That means that 0.7 of the entire mixture is steam. And you are told to find the enthalpy of the system. They've given you the temperature and then the pressure. So what you can do is that you can come to your table or you can use a relation, but usually you can come to your table. You can read the enthalpy of the liquid. You can read the enthalpy of the vapor as well, right? No, sorry. This is the enthalpy of the vapor. So the enthalpy of the liquid is the HF. Enthalpy of the vapor is the Hg. You can put them into that expression with the steam quality and then get the enthalpy of the mixture. The HFG is the difference in the enthalpy of the vapor and in the liquid. So it's Hg minus Hf. Is that okay? So anything with Fg is just the difference in the value for the saturated vapor and the saturated liquid. Is that okay? So if you look at that, it means that we can replace, I think I have to share the screen again. It means that we can replace this here, the Hg minus Hf, with Hfg. So instead of reading maybe the Hg and then reading the Hf and finding the difference, we can just read the Hfg and put that in here, or the Ufg or the Sfg. Is that okay? So please take note of that. If I have my Hf and I have my Hg, Hfg is just the difference. So it's Hg minus Hf. So instead of me doing Hg minus Hf into the expression we're looking at, I can just read the Hfg value as well. Is that okay? Please, are we all fine with that? Okay, that's good then. Okay, someone says, I'll go over it. So this is the last thing we'll do because it's almost time. So I'll go over it one last time. Then we'll have these examples to try out ourselves. If we get stuck, you can reach out to us and then we'll help you. So tomorrow we'll continue from the superheat testing table and then we'll finish this slide. But what I'm saying is, for the person who said they are not fine with what we've done, are you okay with getting the formula? Like, are you okay with the formula we are looking at? Are you fine with the formula? Okay, so what we are saying is that for enthalpy, internal energy or entropy, these are the expressions. It's the same thing as the volume expression we proved on the previous slide. So if we want to find the enthalpy of a system that has maybe both liquid and vapor, I can find the enthalpy of the liquid part, the enthalpy of the gas part, and if I know the steam quality, I can put all those expressions in there and then get the enthalpy of the mixture, right? But what I was also saying was that these properties, we can read them from the tables, the steam table. So I can read my HF and my HG from the steam table. But Hg minus Hf is the same as Hfg. So sometimes instead of reading both the Hg and then the Hf values, I can just read the Hfg value and then use that instead. So I have my Hf, my Hfg, and my Hg values here. So at a particular temperature, it will be given to you in the question, particular temperature or pressure, you can find the HF, the Hg, the Hfg. And once you know the steam quality, you can just plug everything into this expression we have here and then get your enthalpy, your internal energy, and then your entropy. Is that okay? Please, is that fine? Okay, then that's very good. So we'll end here for today. We'll continue tomorrow. So we would I'm sending the link for attendance right now. So tomorrow we'll continue from here. We'll go over the solutions, right, to these questions. So try them out. I've sent you the material already. We'll go over the solutions to them so that those who got stuck will be found. And then we'll continue with the superheated table. We'll continue with the compressed liquids, refrigerants, and then we'll be done with this slide. And then we'll start with lecture 3. Yes, the Hg minus Hf is the same as Hfg. So please let's fill the form for the attendance. And thank you for your time.